Hi everybody, welcome to Climate Change Calculated Part 2 of our series about climate change. So today we want to ask and answer the question, does the CO2 concentration of our atmosphere influence the global temperature? Right. For that we again take a look at physics. Right. So for physics we can check out the absorption spectra of CO2 and water vapor. And there's also an interesting Wikipedia link about the greenhouse effect, which you can see here. So we can click on it. And we see this nice picture here, which shows the basic effect of the greenhouse effect. Basically, we have the sun shining on the Earth. The atmosphere passes the visible sunlight, heats up Earth, and Earth becomes warm, and this warmth produces infrared radiation, basically electromagnetic waves at a different wavelength than the visible sunlight. And this wavelength in the infrared range is now more or less absorbed by the atmosphere, and in particular by CO2. So going back to our slides. So we can actually then look at the absorption spectra here in this German Wikipedia link, which I actually like better because it has a nicer plot for the absorption spectra, which we can see here. So here on the right-hand side, we can see the wavelength. So here is the visible range of sunlight, and this is passed by our atmosphere. And this is now the reflected light, the infrared, coming from the warmth of the Earth. And here you can now see the absorption spectra of the entire atmosphere. So here you can see that the visible light is passed by our atmosphere. So no absorption. But when we go to the infrared range, you can see there are several broad bands which are absorbed by the different gases in the atmosphere. So here we can see the different contributions from different gases. So on the upper plot, we see water vapor. And we see here in the visible light, it's transparent. But then when we go to infrared, it has several bands which are absorbed by water vapor. Then the next one is CO2, carbon dioxide. And you can see in principle the same effect. We have passing of visible light, and then there are several absorption bands in the infrared range. So you can see here actually water vapor has more of this absorption spectra, but water vapor is basically a consequence of warming up. So this can be seen as increasing the greenhouse effect. So if we have more CO2, we will have more water vapor, which in turn increases on the greenhouse effect. So going back to my slides. So water vapor is basically short-lived. So as soon as it's getting colder, basically we have it come down as rain, for instance, and then it's gone. Unlike CO2, which is lasting for centuries or even longer. So in these plots, we saw that CO2 is transparent to the electromagnetic spectrum of visible light, but it absorbs in the range of infrared, meaning the heat radiation coming back from Earth. So that means the sun heats up the Earth with a visible light, and heat is radiated back into space and as infrared radiation. And this is how a balance is established. So basically the energy coming from the sun and reflected back into space must find a balance so that we don't have changes. But this balance now is actually changed by this increase of CO2, as we will see in the following. So when we have more CO2 in the atmosphere, That means it keeps more infrared radiation on Earth. So we could think about it putting on our winter coat. When we put on our winter coat, it also reflects the infrared radiation coming from our bodies, and it keeps it on our bodies, and that keeps us warm. So when we have more CO2, it's more or less like putting on an additional layer like a winter coat, and that basically keeps the warmth inside, or if you do that in the summertime, it makes you sweat. Right? So this additional retained radiation is called radiative forcing. Right? We can also see it here in this link. And in this link, we also have this formula which allows us to compute the additional power which is kept by this increase of CO2. And this is the formula, and we see there are two variables here. So C is the new concentration of CO2, for instance, the current concentration, and C0 is the reference concentration. So for our purposes, we take the concentration of the pre-industrial levels. Yeah, the result is then a power per square meter. Right. So now we can just plug in the numbers. C0 we saw last time is 280 parts per million. C, the current value, is about 410 parts per million. And that's all we need to get a result. And you can just use Python, or any scientific calculator will do too. Just plug in the numbers here, take the logarithm, the natural logarithm here, and the result is 2.04 watts per square meter, or roughly 2 watts per square meter. Say plus minus 10%. That's actually more accurate than we needed for our estimation. So this is now the additional power from the increase of the CO2 to 410 parts per million compared to the pre-industrial level of 280 parts per million. So to compare, this is about a power of a bicycle lamp for every square meter of Earth. So bicycle lamp doesn't sound much, but we have to take into account it's for every square meter of the entire Earth. So that adds up to a lot. We can also compare it to variations in solar radiation. So the sun is not constant all the time. There's slight changes, but that comes only to about 0.5 watts per square meter. So it's not as much as the radiative forcing of CO2. There are also other effects, but these are even lower. So again, for our estimation, we concentrate on the dominating effect, and the dominating effect here is the radiative forcing of CO2. This basically dominates how our atmosphere, how Earth is heating up. So then we can take this power that we now obtained and use it to answer the question, how long does it take for the radiative forcing to heat up Earth by 1 degree Celsius, which is 1.8 degrees Fahrenheit. So again, for our estimation, we take the dominating effects, and Earth is dominated by oceans, which cover about 70% of the surface. So we concentrate on this part. We focus on the ocean for our estimations, and then we have to take a look at the heat capacity of water. Right? You might remember from school physics that this is the energy needed to warm up 1 kilogram of water by 1 degree Celsius, or 1 degree Kelvin. Kelvin just has a different 0 point, the absolute zero, but it has the same spacing as Celsius. So the unit of the heat capacity is joule per kilogram in Kelvin, or watt seconds per kilogram in Kelvin. And we can take a look at this table of specific heat capacities and see that water has the heat capacity of 4.02 times 10 to the third joule per kilogram in Kelvin. Or we can also say 4.2 kilojoule per kilogram in Kelvin. So water also has a higher heat capacity than the remaining Earth surface. So that's another reason why we can concentrate on it. So we can now transform the units of the heat capacity to obtain a formula for the time for 1 degree warming. So we see that the heat capacity is watt-seconds per kilogram and Kelvin. So now we can just bring watt and kilogram to the other side to obtain second per Kelvin, which you can see here on the next line. So I multiplied both sides with kilogram divided by watts, and this is the equation that we obtain. So now we know how to compute the number of seconds needed to warm up the ocean by 1 degree Kelvin or Celsius. Right, so we know for every square meter of ocean we get the mentioned 2 watts radiative forcing. But the question now, to what depth do we have to consider the oceans? Because we have to warm up not just the surface, but the entire water below it too. So for that, we can look up what the thermocline is, and it's kind of an insulating boundary layer to the deep sea. Right, we can check it out here on this German Wikipedia page, which again I like better than the English one because it has a nicer picture. So here we can see it. So here we can see this thermocline is kind of a thick layer, and in this thick layer we have this insulating effect from the surface to the deep sea, and it ranges from about 200 meters to 1,000 meters. So we just assume that we have this boundary here in the middle, 600 meters, for our estimation. So going back to our slides. So we just assume the middle of the layer, or at 600 meters, as the limit to which the energy penetrates from the surface. So now we have a good answer, a simple answer, which also allows us to easily compute our desired result of seconds per degree Celsius. And we know that water has a mass of 1,000 kilogram per cubic meter. Right? So 1 cubic meter is 1,000 liters, 1 liter is 1 kilogram. And for each square meter and 600 meter water depth, we have a water mass of 600 meter times 1,000 kilogram per cubic meter, and cubic meter cancels, so we have 600,000 kilogram per square meter. So for each square meter we have 600,000 kilogram water below it. So for each square meter we need to warm up this 600,000 kilogram or 600,000 liters. So that's a lot, right? We have basically our bicycle lamp, and then we have those 600 tons basically that we need to warm up. Yeah, it's kind of hard to say what it is, but we can still use our formula to get a result. So even though we have large numbers, the formula still holds. So we can just plug it in. So the second per increase in Kelvin is C times kilograms divided by watts. Or if we extend both sides with 1 over square meter, we have C times kilogram per square meter divided by watts per square meters, and this is actually the numbers that we just obtained. Right. So here this kilogram per square meter is our 600,000, and the watt per square meters is the 2. So we just plug it in here. Here is the C. This 4.2 times 10 to the third joule per kilogram and Kelvin. Here we have our 600,000 kilogram per square meters, and then here the 2 watts per square meter. Then if we compute it, we get the result of 1.26 times 10 to the 9th seconds per Kelvin. So 10 to the 9th is a large number. It's hard to imagine what it means, so that's why it makes sense to convert this time in seconds to years. So we just have to know how many years is this number, right? And for that we have to just compute how many seconds does 1 year have, and then divide by this number to get the number in years. So 1 year has 60 seconds times 60 minutes times 24 hours times 365 days, roughly. And that's 31.53 times 10 to the 6 million, times 10 to the 6 seconds. So that's 31 million seconds. So now we just take our result and divide it by 31 million to get the time in years. And the result here is 39.95 years. So we round it up to 40. So that means over the last 40 years, we would expect a heating by about 1 degree. And we can check it out. And indeed, from 1980 to 2019, we indeed had an increase of the global temperature of about 1 degree Celsius, which we can see next. So this tells us this is actually a good fit. So we did a good calculation here. So now we compare it with historical temperature values. And again, we can use open data to obtain those. So they are usually given as relative temperatures because the absolute temperature for Earth is kind of hard to measure. But relative temperature is much more precise because then we just need to measure the difference to the previous years. So here's one plot from 1880 to the present as a comma-separated file here in this link. Or for the last 1,000 years, we have this website here. And this website also contains a link to the past 2,000 years. So when you scroll down in this link a little bit, you have to search a little bit, and then you will find a comma-separated variable file, which I modified a little to make it readable for Python. So here I made this file here, _py.csv, and this file I also put in the link to this video so that you can also download it and play around with it. So then I used a Python program to combine those two data sets, the longer history and then the shorter history. And this is also practical to check the precision of the numbers. If you would see the newer data and the historic data don't fit, then we know there's a bad accuracy. But if there's a good fit, we know there's a high accuracy. So then we plot those two data sets in this program which I wrote, dataplot twinplot2.py. And you can also download this Python file from the link of this video. Yeah, and it actually plots on two curves. The blue curve represents the combined temperature data of those two data sets. And then I also plotted the CO2 data on it for comparison. Right? And we see that our today's deviation from the temperature from the annual mean is already bigger than during the small ice age in the medieval time, and much warmer than at the time of the Roman Empire. So sometimes I heard comments, oh yeah, the Romans also had it warm. Actually, when we look at the data, they had it warm, but not as warm as today, right? So here we can see the plot. So the blue one is the temperature data, and here we can see the data from the more recent times, starting 1880. And you can see there's actually a good fit. So that shows they have a good accuracy. And here you can see the CO2 data, the CO2 plot. And you can see that there's a nice correlation between the CO2 and the temperature, particularly here since about 1750, so in the time of the industrialization. So we see the CO2 basically explodes, it increases exponentially. And now the temperature curve is following, right? So it's now also starting to rise. Yeah, and we can now also use the plotting abilities of Python for zooming in to some interesting part. So I did that here and zoomed in to the time of about 1930 to 2019. And here you can see the result. Again, the red one is the CO2 concentration in the atmosphere and the blue one is the temperature. So again, you can see a nice fit here. And you can see that from about 1980, we have roughly 0 degree relative temperature, to 2019, where we have roughly 1 degree relative temperature, that we have, so from here to here, we have maybe a little bit less than 1 degree increase. So it's about as much as we calculated. And keep in mind, we calculated the radiative forcing for today's CO2 level. So we would actually expect less because in 1980 the CO2 level was much lower at about 320 parts per million. So if we want to really make it more accurate, we should have taken this medium value here of the CO2 concentration. So actually the last 40 years already increased in temperature a little more than we would have expected. Yeah, so that shows that we're on the right path for our calculation. We indeed captured the most relevant effects using the ocean as the most influencing part, and the radiative forcing. Right, so this leads us then to the conclusion. We see that our estimation shows that the global temperature rise is indeed caused by the increased CO2 concentration using physics, radiative forcing, and heat capacity of water. And then with the further emissions of fossil CO2, the radiative forcing will continue to increase, right? We just computed it for today's value. If this curve continues to rise, we have ever increasing radiative forcing, which means more power is left on Earth. And the temperature rise accordingly will accelerate. So the time for 1 degree increase will shorten. So this is also important to keep in mind, and this also shows why it's important to take action. That we really have a problem if we just continue as usual. Okay, so that's it for today. Next time in part 3 we will treat the risk analysis. What can happen if we just continue like today? So see you next time. Goodbye.